We are still pioneers. We've barely begun. Our greatest accomplishments cannot be behind us, because our destiny lies above us.
The initial impetus for the project had been to say, why not examine real possibilities? Why not actually look at the real science there?
Luckily, we had Kip, and Kip is the foremost authority on all things gravitational.
The warping of space inside here scatters some of it back, glides scattering off of the surface of a rippled ocean. Neither wormholes nor black holes have been depicted in any Hollywood movie in the way that they actually would appear. This is the first time that the depiction began with Einstein's general relativity equations.
The visual effects department under Paul Franklin and everybody at Double Negative took Kip's mathematical data and they created real visual representations of what a black hole is meant to look like.
The collaboration has produced visualization of things which nobody had ever managed to do before. You know, we potentially may have discovered a couple of new things that were lurking there inside the mathematics, inside the physics.
I worked out the equations that would enable him to do the gravitational lensing. And so you have light that comes from a star behind a black hole. It may come in, go around the black hole several times, and then come to the camera. And so you wind up with several different images of the star.
The black hole warps the space so much, it just looks like you're looking at a strange sort of funnel in the sky with this intensely black circle at the middle of it. But the gravity of the black hole draws in all the matter from the surrounding universe. And this spins out into a giant disk around the central sphere. And as it whirls in towards the center, the gas gets hotter and hotter. And this thing, the accretion disk around it, shines brilliantly. And then we found that if you then render this whole thing, you visualize it all through this extraordinary gravitational lens, the gravity twists this glowing disk of gas into weird shapes, and you get this extraordinary sort of rainbow of fire across the top of the black hole.
And I saw this disk wrap up over the black hole and under the black hole. I'd known it intellectually, but knowing it intellectually is completely different than seeing it, than feeling it.
We had determined when we started down this road that if it didn't look like something that would be comprehensible to the audience, we would have to manipulate it in some way. But what we found was, as long as we didn't change the point of view too much of the camera position, we could get some very understandable, tactile imagery from those equations. They were constantly surprising. Spoke to the maxim that, truth can be stranger than fiction.
We're going to write several technical papers about this. One aimed at the astrophysics community, and then something for the computer graphics community, saying, here are some things that we've discovered about gravitational lensing by rapidly spinning black holes that we never knew before. So this collaboration isn't over until we've given some sense of the things that we've learned.
Okay. Well, good evening, everyone. Welcome to the November Ottawa RASC meeting. My name is Mike Modam. I'm joined here with Chris Tarrant, who on the drums, who's manning the presentation, and of course Art and Ann Fraser, who's manning the membership booth and the coffee and cookies that we have in break and after the meeting, and of course Eric and Eunice Kajula, who are our videographers, who do a fine job here. For those folks recording the meeting and streaming it live over the internet. For those folks who are joining through the internet, curious to see where you're all connected from. I know Mike Wirfs, you're aiming to connect from Baja, California. Let us know if you're able to do that. And anyone else far and wide, to send us an email and send me an email. And curious to see where you're all connecting from. Okay, up tonight is we've got two main presentations, and I'm quite impressed with the amount of preparation that was done by both Richard Alexandrovich and Rick Wagner. Both of them put in a ton of time. I'm really happy about that, but I'm a tad concerned as well because there's a lot of dedication, a lot of toil, and I suppose labor of love as well. So thank you both for that. So after the Ottawa Skies segment that Gary will be speaking to, Richard will talk about Epsilon Aurigae, which I think many of you know is an interesting phenomenon where every 27 years a star gets eclipsed for a period of time. Rich will talk about, he's been reviewing the literature, and he'll share the latest findings. We'll have a break. During the break, April Alexandrovich is going to be handing out the door prize tickets. So she'll be up front here. Pick a ticket, leave a ticket behind, and at the end of the meeting, we'll make a draw for the various door prizes. After the break, Rick Wagner is going to talk about his presentation on observing stars and their brightness and what you can learn about the health of stars. Okay, another really well-researched presentation. We've got some very interesting observations, lots of announcements, and I know we're going to say it a couple times tonight, but I wanted to say it just right at the beginning, and I'll repeat it a couple times. We're selling the annual dinner tickets tonight. Okay, Gordon Webster's selling them. He'll be probably right outside the theater here. We're selling the 2015 calendars. Same story, right outside the theater. And I'm going to be talking about the free telescope clinic. So I think many of you probably received a note about the telescope clinic. So if you're interested in that, I'll be talking more about them. I've got various sign-up sheets, more details later. Okay, so we've got quite a few new members, 6 new members. Mary Michaud, John Parsons, Ghislaine Cerise, Sayuri Sarada, and Mark Walker. If you're here tonight, welcome. If there's anybody who's here for the first time, it's also nice to have you here. And we've got a great program tonight, and next meeting is an awesome program. I'll be talking more about that. So thanks to all the new folks and the new members. Members in the news. Okay, we've got 2 things. Brian McCullough, if you can come up. I know you're here. So, well, actually, I won't even talk about it. Brian, I'll let you take it.
Okay, thanks, Mike. Ottawa Centre does a really good job about recognizing members that have had some kind of accomplishment through a publication or through a broadcast of some sort. Mike contacted me last night to ask if I'd do a little presentation concerning our Ottawa Centre member, Mike Worths. Mike lives down in Baja, California, and I hope, Mike, you're watching live on TV tonight. And I won't say that it's an honor for me to be able to present this, because what's happened is Mike's got a couple of images in Beautiful Universe magazine, and I'll mention more about that in a second. Now, I say it's not an honor because you think that Buddy could have taken the trouble to truck up from Mexico to show his own stuff on RASC night, but here we are, okay? So anyway, seriously, this is a great pleasure for me to do this. Mike, as many of you people know, takes wonderful lunar images, and he's a great guy. He keeps active from south of 2 borders. So what we're going to do is we're going to start off the Beautiful Universe magazine. It's available now in chapters, and basically what it is put out by Sky and Telescope magazine, and it's a showcase for really superlative astronomical images. All right. So if we go to the next slide, please. All right, so I put this map up here to show you. We'll start off. Mike's got 4 images. He's got 2 in the magazine, and we also managed to get 2 others, so this is really great. The first one, Mike's going to be looking down in the southern highlands area of the moon. So here's north, here's south, and we look at this just like on a map of Earth, east and west. So here's going to be looking at the main item. Here is going to be the crater Clavius. It's actually a flooded plain, and here's Tycho. So when you see the big rays on a full moon, you see the big impact rays going around, it's usually Tycho is what you're looking at. Okay, the second one, he's going to jump right up to the northern region there, to the Bay of Rainbows, Sinus Iridum. A lot of people call it Sinus Iridium, but there's no second I in it. Sinus Iridum is the Bay of Rainbows. And he's looking at the area here, Bay of Rainbows, and the frozen sea, Mare Frigoris, up top. And the next one is coming down toward the Sea of Humors, Mare Humorum. He's going to be looking mainly at the crater Gassendi, and then the second group that he's going to be looking at is the main part of Mare Humorum. We can go to the next one there, Chris, thank you. Right down there. So I just wanted to locate these for you. But one thing you have to understand is this image, when we see it, it's going to be north is going to be up just like it is in this version, except it's been flipped left and right. I think this is just Mike messing with our heads here, but it gets better. All three of these shots have south up. So we're going to see those three shots twisted up the other way. All right, so let's have a look at what he's got here. All right, so here's the first one. So we're looking right down on the highlands region of the moon. A lot of impact craters there, not a lot of areas where there was a lot of lava flow, like we see on the main seas, the mare. But what we have here is the main crater Clavius. All right, now Clavius, and it's got Porter and Rutherford craters cutting inside here, and it's a beautiful area to look at inside here. It's actually a walled plain. It's large enough at 225 kilometers in diameter. It's large enough to be classed not just as a crater, but as actually a plain in its own right. Down here, this is the crater Tycho, which is only it's 85 kilometers in diameter, but it's nearly 5 kilometers deep. So if you were running across here and you tripped over the edge, you'd be going, ah, for 5 kilometers on the way down. All right? So this is the one when you see an image of the full moon, you see all these rays shooting up the ejecta rays, and it's very stunning. The thing that bear in mind when you're looking at these images, if you can look at them, I think they'll be available probably online later, look for the little details. Mike, when he's, these images up here don't do them justice. When you look at them on your own computer screen, you're going to be looking for details in the floor of Clavius here, and this is usually one of the tests that they give you for if you've got a small telescope. How well can you see with your small telescope? Have a look at Clavius. There's a lot of good definition in here, especially when you're getting toward the last quarter phase, so just when the left-hand side of the moon is lit up. Okay, so we'll go to the next one. So here we are in the Bay of Rainbows. All right. And where we are is when we showed on that on the main image there, all of this down below here is Mare Imbrium, the Sea of Rains. So this is a huge impact basin, and over hundreds of millions of years, we had lava flooding up inside this excavation. And what you see here is you can see what they call wrinkle ridges. And this is some very good examples here where you had successive floodings and everything then cooled and contracted and shrank. Right? Along here, this is a really gorgeous area to explore. These are the Jura Mountains, so Montes Jura. And you're going to see a lot of good definition in here, and it's a very steep incline. And you don't see an awful lot of that on the moon. A lot of the areas, as you go up to higher elevations, are usually on a more gradual slope. Up here, this is the frozen sea that stretches across the top of the moon. Right? So remember, west is that way now, and east is coming back this way. But a couple of neat craters here. You can see Bianchini is right here, and Harpalus. So there's quite a contrast in these when you start looking at the way they've been excavated. And if you look at them, if you have a chance to look at them through a small telescope, those two are a good comparison. And you get into Sharp across here, this crater here. What's interesting is this size similarity across these four craters. And it makes me wonder sometimes if they came down as part of chunks flying down, hitting the moon about the same time. All right, but here we are in the Bay of Rainbows. Mike wanted to point out that the Chinese lander, the Jade Rabbit, Chang 3, landed just down here out of the picture in almost a year ago. It was December 2013, right? And, okay, and I think we'll go to the next one. All right, this is the crater Gassendi, and this one that cuts into it's cleverly named Gassendi A. All right, so this is Mare Humorum, the Sea of Humors, going up this way, and remember we've got the upside down image now. All right, so south is up, but we've got this beautiful basin that was here, a nice roundish impact basin, the Sea of Humors. But out here, we've got a much larger area, and you'll see it when you look on the map of the moon. It's the Oceanus Procellarum, right? So you've got this grand ocean. Of course, it's an ocean of what? Of lava, right? From when the moon was still warm inside, and you had rivers of lava bubbling up through rills and cracks and filling these things up, these basins up like swimming pools, and then everything cools and solidifies. But you can tell this is the way planetary geologists start dating the age of things. They start looking, well, what was the order of events on here? Well, we know that this crater Latron had to have been excavated at some point, right? We can see the edges of it here, but we also see that it's flooded. So this is referred to as a flooded crater. So that tells us that one level of flooding had to have happened. I mean, it's all logical, but it helps the planetary geologists put an order of events. Well, if we had that impact first, and that one appeared to have happened about the same time, then what are the things that connect them? And you can start to tell the story of the moon. So we're looking at something that's about 120 kilometers across here. The thing to look at in Gassendi, and this is a number of years ago, I wrote an article, The 7 Easy Steps to Sketching the Lunar Surface in Real Time, and it was crater Gassendi is what I used as my model. But if you start looking in there with your telescope, look at these little rills, these cracks in the floor, in the floor of the crater there. A lot of good detail there. Gassendi, because of its size, here we're looking at about 120 kilometer diameter. This is about 110. So it's classified as a walled plain. Anything up over about 50 kilometers in diameter, you would start looking at that in terms of being a walled plain rather than just a simple crater or a complex crater. All right, we'll go to the last one there, please, Chris. All right, so here we are. Crater Gassendi is just down here. So now we're looking a bit farther south, and you can see more evidence of flooded craters, right? A number of them going along here. Okay, Doppelmayr here. What's interesting is the wrinkle ridges in here. So we can see there have been successive floodings and solidifications and shrinkage. The other thing that's really interesting is you have these rills, basically these cracks in the surface, and there are three types of rills. You can have a sinuous rill, which just snakes along. You can have a straight rill. You can have what they call an arcuate rill, and it's just a very smooth arc. And this is what we start to see right here, about 240 kilometers of a channel that's probably a couple of kilometers wide. So it's just between two fault areas, and the area between has dropped away. All right. So when you're looking with your telescope, look for details like this, and sometimes you're going to see differences in coloration. So you can see even on here, you see some of the lighter areas picking up the sun at a different angle, and you watch this over an hour, it'll change completely. So that's a really good exercise, but it's also, if you're sketching, sketch fast, so because that's what's putting your timestamp, right? The shadows are what are putting your timestamp on. So Mike has given us some really excellent different areas to look at and to focus on, and just by way of more or less closing off, this area here is one of the lunar lakes, and it's called Lacus Excellentii. And I think that it's actually Micus Excellentii for sending us this stuff. Now, what I've brought here is, Mike doesn't know this yet, but just hours ago, he actually bought a copy of Beautiful Universe. I'll be hitting you up for this, Mike, okay? So I'm thinking that maybe for the very first door prize that we have, we'll draw one ticket. This prize can go then, and then the ticket go back in the pail, and then for the main draws. Is that all right?
Sounds good.
All right, and so congratulations to Mike for, he's got a couple of nice images in here, and I have to tell you, to get into a publication like this, you can imagine how many people were contributing to this. It's a real achievement, so I take my hat off to you, Mike. There you go.
Thank you, Brian, and I appreciate you doing that without much notice as well. I really felt that Mike Wirf's lunar images required the right kind of discussion, and Brian's the one to talk about it as one of our moon experts here. Some sad news that follows. Next slide, please, Chris. Thanks. Jacques Lebrec passed away recently. I know a number of you may know him. Rob is going to talk about this.
I don't think there's a lot of gray hairs here, but not too many white hairs. And when I started getting interested in astronomy, my father used to drive me to the Dominion Observatory to look through the 15-inch telescope. And I was probably 10, 12, something like that. Then my father gave up driving, and I ended up taking the bus. But what was interesting there is there's a number of people that were there, and Jacques was the last one. And the first one was Mary Gray. and she was the astrodame for Ottawa. She died quite a few years ago. Then there's another one, was Dick Taylor, and he was operating a telescope. And then there was Jock, and he built telescopes. Of course, the others, Dick Tanner also built telescopes, but Jock was very quiet. When he's very quiet, people that if you're in the room with 3 people, you wouldn't notice him. But he was an artisan. He was very, very good with optics. He was meticulous. And then, I don't know, I guess a number of you people have teenagers. I've got a teenager. And here I was as a teenager, and he actually volunteered to drive me to a General Assembly in Hamilton. Could you imagine sitting in a car with a teenager for 6 hours? Anyway, so that was Jock. That's when I began to know Jock. And then as he started to contribute a little bit, always in the back scenes, in the background of the Ottawa Centre, it was delightful to see him around. He always had this slight little smile on his face. You're not quite sure what he was thinking, what generated that smile. When I finished my 24-inch telescope, he came out to look through it, and he looked through it. This is after I was very proud of it. And all he did was he had this little smile as he walked away. And I don't know whether he said, "Boy, do you have a lemon," or what. But anyway, I was happy with it, and I think he just felt, if I'm happy with it, that's all that matters. But then, as time went on, I started to actually be one of the outreach people at the Museum of Science Technology, just on call. And Jock was on call as well, and he built a wonderful Maksutov telescope that I don't know if they still use there, because I'm not one of the outreach people anymore. Brian would probably know if they still make use of this small Maksutov. But it's interesting point that he also made a photographic Maksutov telescope, and he had the same, idea about optics. Telescopes should be used. John A. Brashear built telescopes to be used. John A. Brashear built the 15-inch telescope. So Jacques also made a Maksutov photographic telescope that was used at Spring Hill Observatory, and it was designed to be used, and it's in storage. And this is why I hope his Maksutov, which he designed for the public to look through, is still being looked through. When I looked through that, when I was doing some outreach and they set the thing up, you have Epsilon Lyra, the double star in Lyra, and you look at it and you can count how many airy disks of stars airy disks were between each of the 2 narrowest components. You could actually see dark space between them. It was remarkable. And so that just shows off his ability as an optician, and again, very, very quiet. He certainly doesn't do a song and dance like we tended to do, certainly as Brian does at the museum. So anyway, I've lost touch with him, I guess, for about 15 or 20 years. The last time I was there, he silvered one of my mirrors. He did it for free because he said, "Can you supply me with some silver nitrate?" I said, "Oh, I think so. I'll do it for nothing." So it turned out that I gave him a bunch of silver nitrate, and he said, "Oh, I should be paying you because of all the silver nitrate I gave him." He gave a beautiful coating on the optics, and always giving tours of his latest little ideas in his basement. His basement itself, I think, was a tinkerer's dream, with little lathes, tools everywhere, optics everywhere, and so on. So I was rather sorry to hear that he had passed, but I must confess he's been around for a long time. He's almost a fixture in my memory of the Ottawa Centre. And he's also one of the premier people, some of the first people that joined and created the Ottawa Centre. There's not too many of them left. So I'll remember him as he was when he was a more vital person. He died when he's 92, and that's a rich, rich life he's had.
Michelle?
Yes. His son Michel is still at the Museum of Science Technology. He was also outreach doing astronomy, and now he's doing other things in the museum.
Well, thank you, Rob, for that great dedication. It's we hate to see them go, but 92, it's a pretty good age for sure, and we thank him for all his great service, especially with the beginning of the Ottawa Centre. So it's my great honor, because Al Scott is not here, to bequeath to you the election of the officers, councillors, national reps, meeting chair. That will take place here next month, December 5th, I think toward the end of the meeting. It takes about 30 minutes. We try to keep it short, but we do have to have our elections of officials. Next slide, please. And so far, this is the slate, as I say, so far. Gord Webster for president, Tim Cole vice president, Chris Tarrant, who never leaves as secretary.
The Greens are all, he's not allowed to leave.
Not allowed to leave, that's it. Oscar for treasurer, Yves Demers, Carmen, Stephen Norris as councillors, meeting chair again, sorry, Mike Morgadam, and Rick Wagner as, and Bill for national council reps. National go to Toronto or go on the phone. It's about a 6-hour meeting. It's done on Saturday, so even time is taken right there too. And I'm past president. I've been shelved. Just like Pluto, I've been shelved. Good thing or not, I don't know. Put me out the pasture. I don't think the wife would like that too much.
But Pluto's a dwarf.
No, I'm not a dwarf. I'm a big blue giant right now. Okay, next slide, please. So nominations may be submitted for any position. This is not closed. You have until November 30th at 8 p.m. Eastern Time to get to Chris Tarrant if you want to have your name on the ballot for sure. Members must be in good standing, means paid up. Okay, you must have your card, must be an active card, and supported by 2 members. So good luck. If anyone has any questions, please see one of our names over here. It's not a deadly position. It's a great honor to be part of the Ottawa Centre, because you are in the decision-making of this great centre, such as SmartScope and any other great programs that will be coming up. So it's not very time-consuming, but it's a great honor for sure, as I've had a great honor for the past 2 years being your president. And for the appointed positions, we have Estelle as librarian, Chuck O'Dale as webmaster. As you see, Astronauts is still open. Still have an opening for Astronauts editor. So anyone with some kind of background in not really editing pretty well, please step forward. Ron St. Martin, Fred Lawson, Observatory Director. SmartScope is Jim Maxwell. Still light pollution, public outreach, and Art Fraser, who do a great job out here every month, serving coffee, tea, to meat for the cat, cookies, whatnot. So they do a great job. And Art also with memberships. He'll give you a membership card once you join. And joining is online. It's very straightforward. Just takes the plastic card. Next slide. That's it. So that's it for, and I guess now into my spiel. Not yet. No.
One slide to go.
One slide to go.
For Mike.
I'll just wait back here.
Okay, folks, one of the privileges I have in my position is to elect or to award the Paul Commission Observer of the Year award. So we base that on images that have been submitted and also observer logs, so that are shared. So if you wish to apply for this award, send me your observer logs before Sunday and a day. And I apologize for letting you know so late here. And we'll be announcing the award at the dinner next Friday, I believe, right, Gary? So one thing I forgot to mention, by the way, I was going to, Chris and myself were going to ask, is can people here at the back sound okay? All right, terrific. As you know, we have door prizes and so forth. Somebody actually has this little R2-D2 planetarium projector. Who brought that? Thanks very much for doing that. So. Pretty cool. It's going to be, we should almost try it out here. I see what it looks like. I presume it hooks up to a PC, does it? Standalone. Standalone?
It's basically a glorified flashlight.
Oh, with a battery powered, is that the deal?
So, yeah.
Oh, very cool. Well, thanks for offering that as a door prize. All right, next slide, Chris, please. Gary, back to you for Ottawa Skies.
I'm back. First of all, how many people have never been to the annual dinner? Have not been to the annual dinner? Oh man, you are missing a feast. Believe me, I can speak for the feast. The second and third year culinary students that do the buffet, so people that have been, check with them. It's really worth the price of going. $42 per ticket. Great speaker, via Tim Puckett. Door prizes, lots of great door prizes, and the food. Oh, the food. Excellent. Okay, next slide, please. Well, I guess it's explosion night tonight. We're going to hear about a couple of stars, whatever, and now we have a couple of stars in distant galaxies. Toward the end of October, October, we have one supernova, NGC 4080. It's a spiral galaxy in 49 million light years away. It has 13.7 magnitude, and it's a type 1 supernova. Okay, next slide. And the day after, now we have one in M61, a lot brighter. M61 is 9.2 magnitude and 60 million light years away. So these should be fairly easy to see. Not the best for sure, but go out and check them out. Okay, next slide. As you can see, that the, if I don't screw this up, middle one. Oh, I did again. Oh, thanks, Chris. So we have the two galaxies, one top, one bottom. So one's in Coma, one's in Virgo. So it's in the morning. It's kind of low in the sky, but still we have two out there, not semi-close to each other. Okay, next slide, please. And the difference of supernova, they come in various varieties. The type 1 supernova is we have a small neutron star, very, very energetic, very strong, very close to a companion, very old star, like a red giant, that can't keep itself together now. It's just so old, and the gas starting to fluff off. Well, the young guy now begins to steal material off the bigger guy. And an accretion disk forms, as you can see in the white. And then after about maybe 10 trillion degrees of heat inside, it bursts just like a balloon. Usually the star stays intact. We're not sure about this one guy, if he's staying intact or not. But they usually stay intact and just go through the whole process over in another couple of hundred years, whatever. So it's robbing from the old and frail. And the type 2 supernova is the cataclysmic, earth-shattering kaboom, as Marvin Marshall would say. This is a star that would be easily 8 or 10 times the size of our sun. Imagine the sun is made of mostly hydrogen, helium, very, very light gases. The core is iron. So that's a lot of compression. And in stars like this, when you have the pancaking of material, when the fuel is used up inside, it hits the inner core and then bangs right out. Loses about 90% of the star itself. So that's a number 2. But these two that we saw are about number supernova type 1. That's the difference. Okay, next slide, please. The only pretty well Kodak moment we're having is on the 13th of November. That'll be on the 13th. Early, well, in the morning, pretty well all night long, because Jupiter does rise about 10 p.m. now. And we have the nice third quarter moon, Jupiter, and the bright star of Leo itself. So pretty well the only planet that's out there now. Venus is slowly coming out of the sun into the western sky. So watch over the next few weeks, so don't look at the sun, but if you see something bright on the horizon, that will be Venus. And also Saturn is sinking into the sun, so we pretty well lost the planets. Mars is pretty well gone too. Next slide. And all this information that I've just mentioned about the supernova, the charts, whatever, it's in my monthly article, which can be found on the Ottawa Centre website or my website, wondersofastronomy.com. Also follow me at AstroEducator on Twitter. Next slide, please. And since I do have to leave early, I can't stay for the whole meeting. Just showed the one gallery shot that I've taken, the massive giant sunspots of AR 2192. It's many times the size of the Earth, and it's actually moved out of the view, and now it's rounded the other side, but it's so large that we should see it come back in another about maybe 10 days. But the next spot that's coming around the corner is 2205, which is giving a lot of flares. Did that again. Okay, third time, that's it, hat trick. Which are giving off a lot of flares, so as it's moving closer to the center point looking at Earth, we might get aurora. We haven't had that huge, except for Eric, that caught some great auroras. Eric, I'm talking about you. That's just in great auroras that one night that Joe Bonner and I came to my place and we saw no auroras, so it was so dark, but he was lucky to get it. So keep watching spaceweather.com on any chance of seeing great northern lights. Next slide. And here's just your favorite lunar phases. As you can see, the full cold moon will be on yesterday. And that's it. We'll see you next month. Oh, we'll see you at the dinner. See you at the dinner, right, folks? Is that a promise? Okay, let's hope. Okay, thanks.
Thanks, Gary. Gary, did I hear you right? AR 2192 is still alive and
Oh, it's on the other side.
It's on the other side?
It might survive and still come back.
oh, very cool. That was quite the sunspot complex. Next up is Richard Alexandrovich. He's going to talk about recent findings on Epsilon Aurigae. Richard.
I'll move this elsewhere.
Good evening, everyone. Now, here's a star system that has interested me for quite some time. In fact, Bob Berman, our guest speaker next month, also expressed some interest when he was looking at it many years ago. It's an object or system, if you will, consists of an eclipsing variable star in Auriga the Charioteer, which is by the name as Erectonius, the son of Vulcan. The brightness range as far as magnitude is concerned is from 2.9 to 3.8 when it gets very dim. Next, please. So here it is, schematically. It's 3 degrees to the right of the 6th brightest star in the sky, which is Capella. And it is the 6th brightest star in the entire sky, and it never sets. Next, please. It forms the apex of an isosceles triangle. It's a group of stars called the Kids. That's the next slide. And the bottom 2 stars are Eta and Zeta at the base of the triangle. And of course, Epsilon, our friend right there in the top, circled at the top. It's very inconspicuous, even in rural areas. I was looking at it a few weeks ago, and it's pretty hard to see, even in a rural sky. Probably very difficult in Ottawa. And as far as the system is concerned, it's one of the strangest and least understood star systems due to its unusual nature, physical nature. In fact, it's been touted as a test for modern physics, and it's been a mystery to observers for some 200 years, at least 175 years. First of all, Epsilon is a variable star. Now, variable stars change in brightness over a function of time. And there are many reasons for these fluctuations. In our case, in Epsilon, it is called an extrinsic variable, which means that the light output changes due to stellar rotation or eclipses near the observer's line of sight. Next, please. The primary is a class F0IA unstable yellow-white supergiant, so they say, that is periodically eclipsed by an object that is vastly larger. The eclipse period on average is 670 days, and it varies from 640 on the low end to 730 days at the high end. This allows observers to make careful measurements via light curves. The time period between eclipses is 27.12 years, which makes it one of the longest orbital periods among eclipsing binaries, which is, if you want to put it in day-wise, 9,892 days. But don't let the star's apparent relatively dim magnitude fool you. The system is about 2,000 light years away, and the main component is some 300 times the size of our sun. So it's a monster. Next, please. Here we have some comparisons of star, Epsilon Aurigae, where are we here? I guess it would be to Ursae Majoris, similar to that size, the 20.8 mass Ursae Majoris. This makes Epsilon Aurigae about 47,000 times more luminous than Sol. Earlier mass estimates placed it around 15 to 19 that of the Sun, so I used Ursae Majoris as a rough example. Interestingly, this system has been a subject of debate for at least 175 years, as I said. Next, please. In 1821, it was German astronomer Johann Heinrich Fritzsche suspected epsilon to be variable when he noticed it dim by nearly 1 full magnitude. Next, please. In 1842 to 1848, the duo of Edward Heiss, a German mathematician, and Prussian astronomer Friedrich Wilhelm Argelander revealed that the star had dimmed substantially in 1847. At that point, the system was garnering more attention, and with it, loads of data began pouring in. The data, which included brightness changes that had varied over a period of between 640 to 730 days. The star displayed short-term variations in light output. That was the main feature. The first detailed study of the star was completed in 1904 by Hans Lutendorf, and that's the next one, a German astronomer and astrophysicist. He suggested that epsilon was an algol-type variable with an eclipsing component, which at that time was unknown to astronomers. Perhaps it may have been a swarm of meteorites covering the F star, which was kind of an interesting idea. And other observers of the 19th century recorded additional dimming events in 1874-75, and then again in 1901-02. But unbeknownst to 19th century astronomers, what they witnessed was a very long period eclipsing binary. Our sun, for example, is unique in that it's a lone star. Many, if not most, stellar animals are born with companions, that is, another component. They are born from the same cold molecular cloud, orbiting in a complex manner around a common center of gravity. Some binaries have orbital planes that lie along our line of sight, or if you want to shorten it, LOS. When one star or component passes in front of another, the combined light from the system usually diminishes. This phenomena is of interest to observers who use light curves to create a story about the system. Next, please. And that's a very simplistic diagram of a red dwarf eclipsing a larger yellow star similar to our sun, and they use a light curve with the primary eclipse on the left, secondary as the star goes behind, and again another primary eclipse as the star comes out from the back and starts its cycle all over again. So usually the light diminishes a bit.
Richard, why is it called an eclipse and not a transit?
You could say transit, you could say occulting, but eclipsing because that's what astronomers like to use most, and when I was doing my research, that's the word that they use most of the time. So we'll just say, I could say transiting, covering up, whatever. It's similar like transiting exoplanet over the host star. So that's basically it. Now, thousands of eclipsing binaries have been cataloged in our Milky Way galaxy. The periods range from Algol and Perseus to as long as 27 years for Epsilon Aurigae. Mind you, Algol and Perseus is only like 2 or 3 hours, so that's very quick. The precise nature of tonight's target has stymied scientists for quite some time. Today, they have a ballpark concept of what is actually happening at the system. However, there are details that need to be worked out. Next, please. Our next astronomer, Harlow Shapley, 1828, American astronomer, surmised that the system comprised 2 stars of almost equal masses. Based on this information, the 2 components should be about equal in luminosity. However, the spectrum of the system revealed that there was no light from the secondary. The bright primary was being eclipsed by a massive unseen companion, and the plot starts to thicken. Next, please. The trio of the 3 great observational astronomers of the 20th century, 1937, Kuiper, Gerard Kuiper, Otto Struve, Bengt Stromgren, if I got it right, had suggested in a paper that the system was an eclipsing binary composed of an F2 star and a cooler and tenuous translucent component. Next, please. This is just a sample of what is happening here. The star actually is cooler. It's not white, so it should be like orangey or red, but it's just a graphic representation of what happens when one covers the other. In this model, the F star was being occulted by the transparent shell star, as they called it, causing its light to scatter via the thin atmosphere of the secondary star. It was once thought that the secondary was thousands of times larger than the sun, called a hypergiant. These are extremely rare animals in our universe. Even exotic ideas were thrown into the fray. Perhaps it was a black hole which was orbiting the primary. But that theory was tossed out because observations revealed no telltale signs of X-ray or gamma radiation. Then in 1965, sorry, I don't have a picture of him, he must have been camera shy, American astrophysicist Su-Shu Wang had published a paper, and in it he suggested the eclipsing body was a thick-on disk or torus of debris. Now we're starting to get somewhere. The puzzle is beginning to get together. Today, it is still used as the preferred model. The orbit of this debris disk is at least 27 astronomical units. That's almost out to Neptune's orbit. The mass is about 14 mass solar, and a radius anywhere from 100 to 2,000 that of the sun. It was enormous. If we consider to take the latter, then the diameter of this object is some 2 billion miles. Now the mystery deepens. Next, please. During eclipse, the star brightens substantially for a short period. In 1971, Robert Woodrow Wilson, the co-discoverer of the Big Bang's echo, tweaked Wang's theory and then suggested that the occulting apparition was a thinner disk of material, but this time with a central gap or opening. This would account for the mid-eclipse brightening as the F star would shine through it. And it was also interesting to note that compared to previous eclipses, the central brightening was more apparent during the 1954-56 event. So, could it be that the central gap is growing or going through dynamical changes? Is it evolving? Another strange thing was that the time of minimum light increased by 64 days, and the overall duration of the eclipse dropped by 44 days. So you can see these things are changing in time scales of only decades. Next, please. Now, during the 82-84 eclipse, the second to last one, the central brightening was the brightest on record. The duration of minimum was the longest, the fading and brightening occurred the fastest, and the F-star companion was changing in time scales of only decades. So who said astronomy can be done in the lifetime of a human being? Next, please. And from 1901 to 1983, a few more years extra, minimum of the eclipse had increased from 313 to 445 days, and of course the overall eclipse period down from 727 to 640 days. In 1984 and 87, they have also recorded, astronomers that is, periodic low amplitude changes of 96 days. Now, still unclear, what lies at the center of the ring? Well, Model A, an object with 4 solar masses. Model B, an object having 15 solar masses, where fierce stellar winds creates a torus around the object, and the center becomes devoid of any material. So there's a little gap there. Model C, a pair of Class B stars in a tight orbit clearing out the central portion of the torus. Next, please. Here's a simplified diagram of what is happening, at least what we know presently about the system. There are 2 stars with a mass ratio of about 1 to 1. Now, someone might be saying, wait, hold a minute, there's maybe 1 star. Well, some astronomers think there's 3 stars there, but they're not sure on that. The jury's not out. So let's go with 2 stars, and then maybe we'll go to 1. Both stars have at least 14 solar masses. That was the saying back in the 1980s. The mass contributed by the 2 stars within the disk explains why the cloud remains intact, why it's not dissipating. So earlier, it was only the F supergiant that was detected spectroscopically because something was blocking it. The opaque disk blocked any light that happened to lurk inside this dark debris disk. During the 82-84 eclipse, next please, the astronomers decided to set up an observing campaign entitled Citizen Sky because they were just getting a little fed up and impatient about what was actually going on here. So they involved 19 countries and 120 observers, people like you and I. And at the conclusion of that campaign, in 1985 at a workshop, the American Astronomical Society meeting in Tucson, Arizona, about 30 astronomers presented papers on the system. Scientists were seeking the exact nature of what was going on here. And also, well, what's the eclipsing object? Today, there is circumstantial evidence, and a lot of it, that the Epsilon Aurigae system consists of a low albedo debris disk. Next, please. I think that's our next slide. Yes. A low albedo debris disk, which occults the F-star, which itself is going through a rapid evolutionary process. In fact, it is dying. The main component is much less massive than previously thought, only 2, maybe 3 solar masses. And in fact, it may be shedding material as it goes through its death throes. As far as objects inside the disk, the jury is still not out on this one, as I said earlier. There can be 1, perhaps 2 stars found in the gap. What they do know, or they're quite sure, it's that it's an upper main sequence hot B-class stars. The disk is about 8 astronomical units in diameter and about 0.6 astronomical units in thickness. The disk is forming via mass transfer from the dying star, so material is being pulled out by the 2 B-class stars, which may be experiencing rapid changes, creating larger gaps between concentric rings. The analogy is similar to the rings of Saturn. The disk is slightly tilted with respect to its orbit and crosses the main component slightly above the equatorial region. Next, please. Okay, we'll just go to that one. And that's another rendering of the system. The F-star, there's a cloud of rotating hydrogen gas, and then that gas is being siphoned off to that disk over there, which is the occulting disk. And then you see at the bottom there the comparison to the solar system and the size of the entire system. It says a central B star. There might be 2. There it's still, the jury's still out. We're not sure about that. So let's just assume that there's 1 for this diagram. So note that the low amplitude variations and decreasing periodicity in the system spectra. They've also noted that, the astronomers. And the reason for that is there may be 1 or 2 hot Jupiters that are spiraling toward its star to meet its maker. Next, please. This is another comparison of a graphic and the actual photograph of the disk covering the star, the F-star, which is the bright orange yellow, and of course the months and the F-star in the circles, and covered by the sort of a tawny-colored or salmon pink-colored debris disk. And just to let you know what's actually happening in the system as the disk goes over different parts of the star. The results from the 2009-11 campaign from the observations from Spitzer revealed that the debris disk is composed of larger chunks of gravel, not smaller grains of sand and dust, and that the mass of the B star is similar to the main one. And the concealed star or stars may be accreting mass from the primary, keeping the torus of gravel stable. Now, there are still questions open that remained. How long has the disk been there, and when will it dissipate? Next, please. This is a graph, simplified graph of all the data points from the system, from various astronomers. You can see they vary slightly, but it's all general. You got the curve starting at the left, dropping down to a low amplitude, a few amplitude squiggles at the bottom, caused by, i.e., a giant planet probably hurtling toward the star, and you've got the brighter part going up in the middle where it goes through the gap, and that's the clearing in the center, the optically thin region, and of course repeating itself again on the right-hand side, and of course ending at the extreme far right. And astronomers, when they do variable stars, they usually like to use the Julian calendar as points of references. So as I said, there are still questions that remain. What's the next slide? How are we for time?
We're fine.
Fine, okay. That's basically an artist's rendering of the debris disk, the opening, the 2 B stars, the 2 diamond-like objects covering the main F star, which itself is dying, and of course it's shedding material. So it's almost like a protoplanetary disk where probably a new system is forming around a large supergiant. So at the conclusion of Epsilon's next eclipse around the year 2038, I hope we're still around, the mysteries surrounding this intriguing system should be settled once and for all. So as far as I think I'll conclude at this point, so if you have any questions. One more slide, okay. Well, that was my closing slide. That's to show what the debris disk would look like around Epsilon Aurigae. Bob Berman was telling me that it's mostly gravel, not small pieces of grain and motes of dust, and it's larger pieces of gravel, probably in the process of forming planets in a very young solar system that is similar to Beta Pictoris and the system around Vega, which is actually the one pictured over here. So I guess that just about wraps it up.
Any comments? Richard, you're looking at chunks the size of gravel. That doesn't really suggest material being pulled off the primary. That's more like, as you were saying, a planetary accretion.
Yes. I tried to look for an image. It's being, actually what is happening, it's being pulled off the primary, but there's that debris disk which is made primarily of gravel and not pieces of dust. So how the gravel came, we don't know. I don't know. I just would love to have that to landscape in the house, because the house value would go really up there. It would be fantastic if I can get some gravel. But anyway, that's the latest report as far as what is around the disk. And of course, there's hydrogen gas. Hydrogen, there was one assumption by an early astronomer that it was ice crystals and clumped hydrogen, but that's sort of, gone down the wayside, and basically it's more like solidified things. I just wanted to show you pictorially what it might look like at the end.
So I just wanted to confirm. So the eclipse itself takes about 2 years, and then the period between the eclipses is much longer?
27 years. It's 18 months, but when they write dates down, it's like 2009, 2010, because there's a period where as it goes out of eclipse, you see, a lot of astronomers, what happens is that when there's an eclipse, they all jump on a bandwagon to make records and observations of it, and not too many of them look at the F star when it is out of the eclipse. They should look at the F star when it is out of the eclipse to see if it's variable itself, because if it's variable, then it conflicts with whatever is covering the star during the eclipse period, which is about 18 months. So when they get a good fix on the F star, they say, okay, this is what's happening to the F star, and then when the disk comes across it, then we could separate the two conflicting data. Any more? So that's 20 minutes, right? 20 minutes? Yeah.
Thanks, Richard. I'm aware that Richard did a huge amount of preparation for this presentation. I think he might have mentioned he contacted, other than Bob Burnham, he contacted a couple of astronomers as well. So this, what you're seeing tonight was a lot of work toiling away, but once again, a labor of love. Very much appreciated, Richard. Thanks for doing that.
All the astronomers might be watching.
Okay, very good. A couple things before we go to a break. I wanted to talk a little bit about the annual dinner, that beyond what Gary talked about. It is open to members and non-members. The price is $42 a ticket. It is located on the Algonquin College campus. There's a couple in Salon D, which is in the bottom section there. You can park in parking lot 8 or 9, and I believe, if I'm not mistaken, the parking is free, even though you might think it's not. It is free. And it should be a good evening, as it has been in the past. Next slide, Chris. All right, I'll do it.
You can't.
Next slide, please. Okay, we're also selling calendars tonight. We'll sell them after the meeting. I know a couple of you picked up a calendars just before the meeting. Price is one for $16, 2 for $30. So we'll sell them just outside the door after the meeting. They usually go pretty quickly here. Very popular. Next slide. A couple things I always like to say, particularly for people who are new tonight, a couple things about membership benefits. We do have an observatory for members, the Fred Lossing Observatory. And actually in January, Gordon Webster is going to be giving a presentation about about the observatory and what it has to offer and what it's all about. So come back in January and you'll hear more about I think a very valuable members resource. We have a telescope alone library, very active, I understand, from Al Scott, who is the telescope librarian. Has lots of scopes out right now, and we continue to receive every couple of months a new telescope that's donated to us. So it's a wonderful resource for members. Next slide, please. We get a number of, with your membership, and I'll talk about prices in a second, there's a number of benefits here. One of the benefits is the Observer's Handbook. Looks like Chris, you put the 2015, you updated this slide there. To show the 2015 edition, which just came out actually. I got mine actually this past week, a week and a half, I think, ago. We have a door prize for the 2013 edition, so if anybody wants to see what this is all about and you're not a member and you want to take a look at it, sorry about that. You'll feel free to come take a look at it, but it will be a door prize. Next slide. There is also, with your membership, a Sky News magazine and our RASC journal. Membership is adult, $72. A family membership is $67 plus for each adult. It's $10 more or $5 more. So first adult will be $77, second adult will be $87, and there's also a youth membership. We can, in fact, I was talking to Art Fraser. We can, in fact, take. If anybody wants to procure a membership, we can do it here tonight. In the past, we've told people you can go to the internet and do it on the internet. We can accept your application tonight as well. We're going to give that a try. We do need checks to do that. Otherwise, if you don't have checks or you don't have cash, we prefer checks because we don't want to handle cash. You'll need to go through the internet or you can phone the national office and directly and give them your credit card over the phone. Okay, next slide. So some of the benefits of being a member, other than these monthly meetings and obviously the impressive presentations that you've seen over the last many years, we've got things that are offered both in our center and offered nationally as well. There is a discount. I don't talk about this much. There is a discount for Sky News and Astronomy and Sky and Tel magazines as well. That's available to members. Next slide. If you want to know more about the various, like the Fred Lossing Observatory, you can email Ron and I say Martin and so forth with the Telescope Loan Library. The reason why we have we do have an astronomy book library that's at the Museum of Science and Technology, but as you know, we're not there right now because of the mold problem at the museum. But our library is based there. If you want to contact these people about, for example, Stephen McIntyre about renewing a membership or getting a Sky and Tel and Astronomy magazine subscriptions, I should say, you can email those people. Their email addresses are at that URL at the bottom there, tinyurl.com and RASC Ottawa. So that's an easy way of remembering that. If you want to copy that down, we can put that slide back up in the break, or if you wish. Next slide. Okay, some humor that was contributed by Bob Hillier, so I think many of you can relate to this. Let you read it. I think a couple of you can definitely relate to this. All right, next slide.
That's not right. You're an astronomer if you bought your car to carry telescopes around.
Yeah, that's right. That's right. Yeah. Good one. Yeah. Yeah, that's right. I think Mike Wirth is going to say something as well. And Gary contributed this one here, a breathtaking view of the Milky Way bar from the surface of Mars. Okay, different kind of humor, I guess. All right, it's still nice to see. Next slide. All right, so April is going to hand out the tickets for the door prizes. She'll be right up front here, and I'll see you. And we're ahead of schedule here, so that's great. So let's come back at let's say 12 minutes past 9. I got 9 o'clock right now. Thanks, folks. See you shortly.
For billions of years, it had been orbiting the sun at the dark edge of the solar system. Perhaps tens of thousands of years ago, no one knows when, a close encounter altered the course of this small chunk of ice and flung it toward a new destiny and a new orbit that would bring it close to the sun every few thousand years. On its most recent passage around the sun, a team of astronomy enthusiasts awaited this comet's arrival with ambitious plans. A project to capture a comet on film as no one had done before. Was the rather wild idea of Peter Ceravolo, a Canadian astronomy enthusiast and telescope maker. The goal? To make a comet come alive.
Back in the 1980s, I saw an IMAX movie called Sacred Sight. It wasn't a very long movie, only about 7 minutes, full of time-lapse motion picture sequences, some with astronomical themes. And one of the segments in that, a 20-second clip, was of Comet Halley moving through the star field. To the layman, it didn't look very impressive, but to someone who understands astronomical photography, I was stunned. For the first time, I saw an object like a comet come to life, as opposed to being a static, two-dimensional thing on a photograph.
The opportunity to capture a comet in time-lapse movies came in March 1996, and the close approach of Comet Hyakutake, a comet discovered only weeks earlier by Yuji Hyakutake, a Japanese amateur astronomer. Hyakutake's comet, like most, is really an orbiting iceberg. A nucleus only 2 kilometers across, pockmarked with jets of dust and gas that erupt into activity as the comet nears the warmth of the sun. Capturing this activity in time-lapse detail was going to be a technical challenge. No conventional camera or movie system would do the job. Instead, Peter had to draw on his optical expertise to design a special photographic system called an astrograph.
The astrograph is a completely custom-designed photographic telescope. Nothing about it is off the shelf, if you will, or readily available. Everything from the optics I designed and manufactured right through to the film holder.
Time-lapse movies of the comet would require taking dozens of exposures every night for as many nights as possible. The result would be hundreds of negatives.
But it became clear to me after not too long a time that turning those little frames, 35mm frames, into a motion picture was going to be one heck of a lot of work, and it required a skill set different than my own. And that's when I did my best to try and convince Doug George that he really needed to be in on this project. His programming skills, his image processing skills were indispensable in turning these still frames into a truly stunning motion picture sequence.
But Peter realized he needed more than just Doug's expertise.
Since Comet Hyakutake was coming so close to us, I suspected it might be possible to resolve jet-like structure coming from the comet. And I suggested to Paul Boltwood that it might be a worthy project to try and produce a time-lapse motion picture of the inner workings of Comet Hyakutake, trying to record the jet structure and changing features very tight into the comet's head. And we were very fortunate that he took the project on.
Paul Boltwood had his own technical challenges, tracking the comet from his backyard observatory. Paul planned to use a 7-inch refractor telescope to image the comet at extremely high magnification. But instead of using film, Paul planned to capture the comet electronically. Paul's project would complement the images the rest of the group hoped to take. Paul, concentrating on details near the nucleus, and Peter taking wider shots of changes in the tail. Comet Hyakutake would pass only 15 million kilometers above Earth's North Pole, then race off toward the Sun. The group would have only a few days to shoot the comet, one chance in a lifetime. As any astrophotographer knows, it's a meticulous process. Equipment has to be aligned with arc-second accuracy. In the dark, in the cold, late at night, it's easy to make mistakes. Dawn, and what would become a familiar chore: taking down all the equipment they had so painstakingly set up hours before. It had been a successful first night. Or had it? The real proof was still in the cameras waiting to be developed. With the moon setting later each night, time for shooting the comet under a dark sky was coming to an end. They had captured the comet on 10 nights, taking over 900 photographs. But that was just the beginning. 900 negatives of the comet, and each had to be digitally scanned. The technique is a new one, combining the 150-year-old process of photography with the latest digital technology. Each negative was placed on an electronic scanner, which turned the image into digital data. Before they could be spliced into a movie, each image had to be enhanced, corrected, cleaned up. Paul had captured more than 2,000 digital images from his small backyard observatory. Weeks of planning, nights of arduous shooting, and months of work at the computer came down to one short videotape.
No, this first part, I like the first part. I have to admit, that first part looks really nice.
You know, up until the night with the clouds, you know, is the best part. And
there's the galaxy, so that little galaxy zooming by.
Oh yeah.
Going to the tail.
You can see the cloud, bright stars going through the clouds.
They fuzz up, and then you see a little hop as I've deleted a number of frames that are too clouded out.
Okay. So that big jump was because of the cloud, because you had to edit out the cloud.
It must have knocked out about half the night, at least.
There comes the dust tail that I like, because of the color contrast with the iron tail. You've got many different appearances. The different nights are all different from each other. We're very lucky on that. This comet really looks like many different comets.
What are those things zooming by there like that?
Satellites. It's got to be satellites.
I thought satellites. I thought they might have been a meteor or something that was streaked through.
No, there's too many of them. They're running parallel. They're satellites. They're probably geosynchronous satellites.
Well, it's amazing the differences. The difference you get when this thing is set in motion.
The brilliant head glows in shades of green and cyan, colors created by molecules of carbon and cyanogen. The most striking feature is the comet's bluish tail, a gas tail waving in the wind of charged particles and magnetic fields streaming out from the sun. As the comet approached Earth, its motion across the sky sped up, making stars appear to streak across the frame faster and faster. Partway through the sequence, a broad yellowish tail appears, one made of dust particles ejected from jets on the nucleus of the comet.
Yeah, here's Paul's sequence.
Look at the jets. You can
rotate.
When did you get the jets?
Yeah, it's just spinning around. Look at
Wow.
the stars zipping through.
Looks like it's raining.
What's that fountain effect? But what happened to the rotation? It doesn't look like it's actually rotating. It looks like it's just blowing stuff off. It's rotating in the first part.
Yeah, that's
and now here, it's going off.
We also got one going right off the screen. We got jets that go right off the screen.
Did you have much cloud?
But they're going this way now.
Did you have much? There's a big transition between this part that's rotating.
Oh, there were
and
nights that
bang,
were
there.
Yeah.
Now the fountain.
Well, there's a couple
that's
nights.
A change of night.
That's more than one night, though, isn't it? The gap?
We've got, yes.
Well, you get a lot of those features in the
Paul's
tail.
high magnification view probes into the bright head of the comet to reveal details in a region roughly 14,000 kilometers across. The 2-kilometer wide nucleus itself is invisible, embedded in the bright glow, but spraying from the region around the nucleus are multiple jets of dust. They had achieved their goal. A group of astronomy enthusiasts had combined talents and resources to bring a comet to life. The images are beautiful, almost hypnotic to gaze at. Reward enough for the effort? Perhaps. But in a surprising turn of events, the movies were to prove to have much more than just aesthetic value. From his office in Tucson, Steve Larson explains some of the science in the images.
So, Steve, these are nice, pretty pictures here, but can you tell us what's going on in a very basic way with the comet and what we're seeing, what's happening?
Well, these time-lapse videos show graphically how comets change in time rather than still pictures. And because they're color, they also show various components of the comet. You can see the head of the comet, which is gases produced by sublimating ices as it gets close to the sun, and also components caused by dust, which are blown back by radiation pressure, which are shown as kind of yellowish, and then ions, which are purplish, that get driven back by the magnetic field of the solar wind. And only in sequences like this can you really see the subtle changes in the ions, which are traveling rather quickly. They're being accelerated back at a couple hundreds of kilometers per second velocities, whereas the dust, for example, is going back much more slowly.
For this comet, the gas tail was the showpiece. This purplish tail is made of ions, molecules of water and carbon monoxide, among others, stripped of some electrons. Like iron filings, these ions can be twisted into intricate patterns by magnetic fields. The waves and ripples we see are an effect of the comet traveling across the shifting magnetic field spiraling out from the sun. They form a visible probe of the space between the planets, a celestial windsock blowing in the solar wind.
Then the sequence that shows the near nucleus structure is particularly interesting because this component is, the brightest part of the comet is all dust, and these are being given off from a rotating nucleus from discrete areas. Mm-hmm. And so you almost get a lawn sprinkler effect for the different active areas as the nucleus rotates.
On the first night, there is a slight clockwise rotation, but on the second night, the jets appear to be shooting straight out. The pressure of sunlight curves the dust jets back in either direction, but with little rotation. As it turned out, on the nights Paul took his images, we were looking down at the equator of the comet. Had we been looking at either of its poles, the lawn sprinkler effect would have been more obvious.
Thanks. So this Yakutaki provided us an excellent opportunity because it was such a close approach.
Yes.
How often can we expect such close approach type comets to appear?
Oh, once or twice a lifetime.
That's it?
Mm-hmm.
That were this bright?
Right. Hope you enjoyed it.
After rounding the sun on May the 1st, 1996, Comet Hyakutake sped away. Returning back to the outer solar system. Its next visit, some 14,000 years from now.
Comet Yakutaki turned out to be the opportunity of a lifetime. Having a comet come by so close, one that was so dynamic, so active, and having the right mix of people, having the right equipment ready at the right time, was extremely fortunate. And then to have the results, the images that went into making the movie, turn out to have scientific value. Scientists have requested copies of the images for research purposes to study the nature of comets. All in all, it's been a truly rewarding experience.
mentioned earlier about the telescope clinic. Okay, so the purpose of this clinic here is to provide particularly new members or people who are new to astronomy. They just purchased a telescope or they're about to purchase a telescope. If you're struggling with the telescope, you're not getting what you expect from it, the purpose of this telescope clinic is to really walk you through the basics. What do all the knobs and all the dials do? Let's review the terminology, help you with polar alignment, help you, explain what collimation is all about. If you need help with collimation, we'll show you how to do it. It's intended to be a real basics. Okay, it's intended to be very much personalized. Richard Harding is running it with an able group of volunteers. Already we have, I think, 29 people have signed up for this. So it's grown way beyond it's attracted much more people than I expected. I've got a sign-up sheet, okay? If you are interested in this, is a free telescope clinic. The plan is to run this on, Richard, I'm always forgetting here, November 22nd, I think, right? Saturday, November 22nd. It's at the North Gloucester Library. Advanced registration is required, so you can either sign up tonight or send me an email and and the kinds of questions I ask are, do you have a telescope? You don't have to have a telescope, but if you do, tell me what type of telescope, what kind of mount you have, if you know, and what kind of questions you have, because we really want to give personalized attention to your particular needs. The other thing too is we're likely going to have to, we expect now that we're going to break it up into 2, possibly even 3 sessions. Because we don't want to have 29 people, and I suspect we're going to go up to 35, 36 people. We don't want to do that all at once, so we want to try and break it into smaller groups with the individualized attention that I think people deserve. So we're going to need a whole bunch of volunteers here. So Richard Harding is here, Attila is here tonight. And I'm really we really need at least 7 to 8 volunteers who can help out with providing that kind of individual support. So answering questions about how to use your telescopes and so forth. A whole raft of questions I've got from people who are asking have specific needs. Others are saying I just can't get my scope to when I try and point it at the sky, it's not going where I expect it to go. Those kinds of things that we also went through. So again, if you're we're looking for volunteers, and really could use 7 to 8 volunteers per session that could provide that support. Enough talking about that. Okay, so over to Rick Wagner, who's going to talk about what you can notice with different star brightness and what that tells you about the health of stars. All right, so Rick, over to you. Thanks very much.
Good evening. I'm cheery this evening. It snowed today. We're in for another good winter. Good evening. I thought I'd talk tonight about some of the astrophysics that we can actually do now with just the equipment available in our backyards. One of my, now do we have control here? No?
Nope.
Okay, next.
It's one of the many gremlins tonight.
Yes. One of my main interests in astronomy is RR Lyrae variable stars. And this is a type of star. It's named for the brightest member of its class, which is in the constellation of Lyra. They change in brightness. You saw Richard Alexandrovich's slide with the light curve. Well, these stars do something similar. Periods generally under a day, even down to a quarter of a day. They change by a quarter of a magnitude up to a full magnitude. One thing that they've discovered about a century ago is that the light curve actually changes in shape. It has a fairly steep rise and a steep rise, slower fall off. And the curve actually shifts on a period of months. And after a century yet, nobody knows why. So this is one of the things I'm hoping my little bits of data will help contribute to a solution. As far as the actual thing that prompted me to the talk tonight is Wendy Friedman and Barry Medore earlier this year published a science paper dealing with Cepheid variables. These are used to determine the distances to other galaxies and stuff. And it was just such a beautifully simple and elegant piece of science, really advanced, but technologically speaking, but something that's so simple and easy to understand that we can do it here ourselves. And I figured I can actually do this with my RR Lyrae stars, and we'll see what happens. So, next. Please, thank you.
Next one, try it.
Okay.
Right button.
Right button. All right, so here's a picture. I have about 1,000 of these. This is my star.
Right there in the middle. That guy. You can use a laser in the middle.
Oh, the laser does work.
Top, yeah.
All right, there we go. All right, that guy right there. UY Cam, camelopardalis. So, before we get into the actual astrophysics that's new, we're going to do a little bit of a background. Oh, look at that. Let's build a star. Take a big blob of galactic material, 1 billion tons, be a nice amount, 75% hydrogen, 25% helium, and about 1% or less of all the other stuff, all the heavier stuff. Squeeze it together, mix it nicely, squeeze it together, and gravity will soon take over, and compress it all into a tight ball. The whole thing heats up, thermonuclear reactions start in the center, and we have a star. Now, the interesting thing to note about this is that all stars get formed the same way. All stars get formed out of the same materials, in the same ratios. So the only thing that's really important in defining a star is its mass. It tells you almost everything you need to know about the whole life of the star. The structure, how bright it's going to be, how large it's going to be, how long it's going to last, what's going to happen to it when it dies, everything. There's a few other little things, like how much heavy elements you have in it. If it's a close binary with another star, there's going to be big effects. And what I'm going to talk about here probably won't apply. But for most stars, mass tells the whole story. About a century ago, Einar Hertzsprung and Henry Norris Russell were working independently, and they both came up with the idea that if we plotted the brightness of the stars against their temperature, we might learn something interesting. So we've got the brightness up here, luminosity is the more scientific term, temperature across the bottom. You'll notice temperature runs backwards. Well, that's because these guys were actually doing it by spectral class, and when you put spectral class in order this way, temperature comes out in order that way. And of course, once one astronomer's done it one way, we all do it the same way, forever. So, the question is, if we're going to plot everything on this graph, how do we get the temperature of the star? Well, we ask our local blacksmith. And he tells us that when you heat up a piece of metal, it starts off cold and dark, and as it gets hotter and hotter, it gets brighter, turns red, gets yellow. If he keeps going, it turns white. And a blacksmith will actually use these specific temperatures to get the metal to the right temperature for the things he's trying to do at the moment. So, now we know that we can probably use the color of an object as a proxy for its temperature. So, the hot stars are white or even blue-white. You can see them up here. The very cool stars are deep red down here. These are the spectra of different stars. So, if we measure the color of a star in two different, or the brightness of a star rather, in two separate colors, in this case we're going to use green and blue, that can give us a good guideline as to its temperature. You can see the cool red star is much brighter in green than it is in blue, a yellow star, they're about the same. And for a very hot star, the blue is actually much brighter than the green. Now, in the astronomy world, they don't call this green, they call this visual, because when it was first developed, the idea was that this should be approximately the same magnitudes as what we see with our eye, which is most sensitive in the green. So this is always B and V. So at this point, you should all be saying, "Oh, cool." There we go. So take your digital camera out, stick it on a tripod, take a 20-second exposure of the sky. All those stars have colors. If you then take that picture and compare the brightness of each star in the blue channel and the green channel, you've now got a pretty good idea of a guideline as to what the temperature of that star is. And in fact, if you then take those and calibrate them against stars that you know the temperature of, like say from the Observer's Handbook, you can actually calibrate it so that then you can actually start measuring the temperatures of the stars with your little point and shoot camera in the backyard. One of the easiest things to do, for instance, Orion is coming up now. Take a picture of Orion. Rigel and Betelgeuse are distinctly different colors. They'll show up quite nicely. So here we have a graph now that relates the color index, our blue minus visual, to the temperature. The actual curve is more of a hockey stick shape, but this is a fairly good approximation. So the next thing we needed was the luminosity. Well, that's easy. That's just the brightness. Except, of course, when you move a star further away, it looks fainter. If you bring it closer, it looks brighter. So we have to get rid of the distance. And this is why it took until about the year 1900 or 1910 for Hertzsprung and Russell to be able to do this graph, was because it's very difficult to figure out how far away a star is, and therefore what its true intrinsic luminosity is. So in our case, we won't deal with that tonight. We'll ignore that problem. And we will just use the absolute magnitude, which is the conventional thing. So here's our diagram. Now this one I pulled out of the RASC journal from about 1998. Cameron Reed did a little paper on constructing these diagrams. I think a year later, Mary Lou Whitehorn actually plotted one of these in the RASC journal. She went through the Observer's Handbook. All the list of the brightest stars all have the absolute magnitudes listed, and the absolute magnitudes are also there for all the nearest stars. And so with the color and the absolute magnitude, you can actually plot one of these right out of your Observer's Handbook. So what do we see here? Most of the stars, almost all the stars, lie on what's called the main sequence. Well, it kind of makes sense if you think about it. If mass is the only thing that really changes from one star to the next, that we should see something fairly simple come out of this. Up to the left, here we have stars that are about 100 times as massive as the sun. They're about 100 times as big in diameter. 50,000 degrees surface temperature, 1,000,000 times brighter than the sun. As we come down, the stars get cooler, dimmer, yellower. Our sun is sitting right in about there. And then as we continue down, we get into the red stars. Down here, the lightest weight stars are about 1/10 of the solar mass. They're about 1% as bright. And their surface temperatures are somewhere about 2,500 degrees. So, what's the implication of position on this diagram? Well, if we have two stars with the same temperature, they must have the same color. So one must be above the other in the graph. So here we have two stars, one right above the other, so they have the same surface temperature, but one is twice as big in diameter as the other. That means it presents 4 times as much surface area, and so it's going to be 4 times as bright. It's not very difficult. On the other hand, This is a little more difficult to understand. If we have two stars that are beside each other on the graph, remember, it's brighter, fainter. So these two stars have the same brightness, but this one is much cooler than this one. In fact, this one I've plotted with about 3,000 degrees surface temperature. This one's about 6,000 degrees. So this one is twice as hot as this one. Well, the physical law for production of energy by a hot surface is that the energy output is the fourth power of the temperature. So twice the temperature means 16 times as much energy output. 1 square meter of this star puts out 16 times as much energy as 1 square meter of that star. So if these two stars are the same brightness, that means this one must be 16 times bigger in area than this one. 16 times bigger in area means it's 4 times as big in diameter. So now we've got an understanding of what the position on the diagram means. So I think that's enough background. Let's plot our star. Oh, well, first, let's measure our star. Okay, so I've taken about 1,000 pictures, 500 blue pictures, 500 green pictures of this star, and I measure the brightness on each picture. And here's what I get. If I fold this is about 0.267 days, and what we do is we convert it into a phase, and then I take every quarter day and I overlay them all together so that all the observations overlap. And I get two nice smooth curves. You can see there's the steep part where it's brightening. Here's the more gradual decline in brightness. It seems to be fainter in blue, but that's actually just an artifact of the filters and stuff. What else? Let's see. Average brightness here is about 11.5 magnitude. So, 4-inch scope will show this guy up. Because there's some scatter on these numbers here, what I've done is you can see there's thin lines in there. I've actually fitted some smoothing lines to the data to make it easier to work with. So we want to get the temperature. So if we subtract the V magnitudes from the B magnitudes, we get a B minus V curve. So this is our color index. And basically what it shows us, if you think back to the, can we go back? Yes, we can. When the star is brightest, faintest at the middle, and brightest. So when it's brightest, it's also bluest. When it's faintest, it's reddest, and then it goes back. This could be interesting. But first, we see the average color here is about 0.28. And we want to put this on our diagram here. Well, it turns out that all the RR Lyrae stars all have about the same absolute magnitude. They're all about 0.7. So they all lie in about this level on the diagram. 0.7 magnitudes is about 4.1 magnitudes brighter than the sun. So that means they're about 40 times brighter than our sun. Means because the absolute magnitudes are all the same, I didn't actually have to measure it, which is a good thing because, again, it's very difficult to get absolute magnitudes. The color, 0.28, is about there. And so there's our star. You can see, here's the main sequence. It's a ways off the main sequence. It would have started over here somewhere and it's drifted across here. So it's an evolved star. It's not burning hydrogen in its core anymore. It's probably burning helium, maybe into carbon and oxygen and stuff. So, and interesting things will have happened to it in its lifespan. If we look up here, we can see it's about 7,500 degrees, surface temperature, and one of the points of Cameron Reed's article was to be able to put on theoretical things like what is the radius of a star. So here we can see here's a radius of 1 solar radius, 10 solar radii. So our star is in here about 4 or 5 times as big as the sun. And does that make sense? 7,500 degrees, that's about 1.3 times the temperature of the sun. which means if we take the fourth power of 1.3, that's about 3 times. It's 4 or 5 times, say 4 times as big in diameter. That means 16 times the area. So 3 times 16 means it should be about 48 times the brightness of the sun. And we found from the absolute magnitude about 43, actually. So we're pretty close. So it looks fairly reasonable. The other problem we've got is, of course, the star is actually changing in brightness, up and down. It's actually changing in color back and forth. So why have I got a dot? Well, it turns out that the changes actually, and just coincidentally, are just about the size of that dot. So let's zoom in and see if we can get a closer look at what this star is doing. Here it is. Now this is actually not the actual numbers. This is from subtracting those nicely fitted curves. And I think these crossings and stuff are artifacts of the curves. The curves don't fit the data exactly. So don't take this literally, but the general idea here is basically almost exactly what Friedman and Medora did with their Cepheid, except theirs was just an open loop. But the point is, down here it's redder and fainter. It gets bluer and brighter, redder and fainter, and it just keeps, this is what it does on the HR diagram through its period every quarter day. So we know if it's getting bluer, it's getting hotter, so it must be getting brighter. Ha! Maybe we've solved our whole problem here. 0.315 is its reddest, and 0.245 is its bluest. So if we go back to our B minus V to temperature relationship and read up from those two colors, we get the two temperatures of the star when it's at its brightest and when it's at its faintest. And what we find is that it's about 7,370 degrees when it's cool, 7,820 degrees when it's hot, about 450 degree change, or about a 6% change. Well, if we take 1.06 to the fourth power, we get a 1.27 times increase in brightness, which is about a quarter of a magnitude. So there's why our star is varying. It's because the temperature's changing. Except our star is going up and down by 0.4 magnitudes, not 0.26. So we're missing about 0.14 magnitudes. Well, 0.14 magnitudes is about 1.14 times change in brightness. If we take the square root of that, we get 1.07, because the size of the star is changing too. That's what's causing the remainder of the brightness change. So we now know that this star is going up and down in size by plus or minus about 4%. So we have a diagnosis. We've measured the brightness of the star in B and V. We've determined that it's about 40 times brighter than the sun and about 4 or 5 times as large as the sun. Its average surface temperature is 7,600 degrees, but it goes up and down, plus or minus 225, and its size changes by about 3.5%. So the diagnosis then is that UY-CAM suffers from periodic minor fevers, some bloating, but on general, it's pretty much a normal star. The prognosis, this is a brief period in the lifetime of a star. As the star continues to evolve, it will go into a more stable configuration, and these problems will stop. Therefore, I don't recommend any treatments. Any questions?
Well done, Rick. Well done.
Thank you. Yes?
Have we any theories what causes this variation?
The Blaschko variation, you mean?
No, the temperature variation.
Oh, the temperature variation and everything, yes. It's actually very well understood. Basically, there's some distance inside of the star, and I've never been able to figure out exactly how far, but within the star there is a certain layer where helium or hydrogen, depending on the type of the star, in these ones it's helium, is partially ionized. And what happens is if that starts to contract a little bit due to instability or convection or whatever, the heat generation goes into ionizing the helium instead of heating up the star, which means effectively the heat gets absorbed and capped. So the heat starts to build up, and that will cause expansion. So the star starts to expand, and it will expand out to a certain point where, of course, it starts to cool. The helium deionizes, which makes it more transparent. So now the heat all escapes. The whole thing starts to collapse and starts the whole process over again.
Thanks.
Yeah. Anything else? Yes?
Hey, Rick, I got a theoretical question for you.
Okay.
Your metal temperature versus color.
Yes.
I was interested in that. It turns white as it's very bright. Do we know of an element that actually turns blue before it melts?
I don't think anything will ever turn blue. If you, I don't know if we can get back. There we are. See, as the curve, as the thing gets hotter and hotter, right, the emission gets higher and higher up here. Eventually it starts producing X-rays and gamma rays, but you still only end up with essentially a fairly steep curve through the visual region. So you always have a fair amount of red light, green light. So I think the best you're ever going to do is something that gets blue-white.
There is an element that turns blue before it melts.
Smart act. All right. Oxygen.
Yes.
Does it?
It's a liquid. It's blue as a liquid.
Oh, okay. There you go. I've never seen liquid oxygen. So.
Quick question over here.
Yes.
I forgot to mention my talk relating to the F-star asymptotic giant branch. What is the clear definition of that?
That's a good question.
Repeat the question.
What is an asymptotic giant branch? And it's one that I must admit I've never been entirely clear on, but as the large stars begin to evolve, they move over here and they form giants. You can appreciate from this HR diagram that, you know, this star over here, you know, might be 10,000 degrees. Same brightness star over here is like 3,000 degrees. So it's 3 times cooler to the 4th power. It's 81 times less surface brightness. So that thing's got to be enormous. And in fact, that's where you find stars like Betelgeuse that are like, you know, 1,000 or 10,000 times the size of the sun. But as they move over here, there's a thing called the giant branch that I think curls up here. And then there's another group of stars, different type of giants or something that and I can't remember if they're forming and moving up or if it's the giants that get up here. I think it may be that the stars come along here and they do what's called a helium flash. They begin to build up helium in the core, and it just sits there. The star starts to contract, and that helium starts to warm up, and at a certain point, it suddenly reaches the temperature where it can start to fuse, and essentially you get a huge amount of helium suddenly fuses in a very short period of time, and so that's called the helium flash, and it takes the star up here. And then I think as that subsides, I think it follows a somewhat parallel curve. That's you know, the term asymptotic is a line that's sort of continually approaching another line. So you've got the giant branch, the giant branch like that, and then the asymptotic branch is one that starts at the same place but comes out in a slightly different curve. And so they're
meanders, right? Because some stars will meander.
Yes. A lot of the larger stars will actually have a helium flash, and then they can have a carbon flash, and Rob Dick is probably up there going, no, Rick, God, no. But so he probably knows better, and we can talk about it. All right. Thank you.
Thanks, Rick. Very impressive. If you actually have more questions for Rick, obviously he'll be around after the meeting. We're going to see Rick again in January. He's doing another presentation on polar aligning scopes, and he's got some interesting material that he's developing. The member images, so we got quite a few here. If people who are sharing their reports, if they could come line up here, and we'll do one after the other. We are a bit short on time, so if each of the observers could go with some speed, I appreciate it.
That works now.
Right button?
Should work good.
Okay, very good. First up is Dave. Dave Chisholm. Right button?
Right button, okay, thank you. Okay, this is my first attempt at doing a little bit of astrophotography. This is a shot taken September the 8th through my Celestron Nexstar 5. And my high-tech camera for this was my BlackBerry, held up against the lens. And it came out reasonably well. You can see the rays coming out from Tycho there. It's a little bit washed out here. There. Oops, that was the wrong button.
Right side.
Right side, thank you. Where's the laser?
Top. Center.
Center, thank you. You can see Tycho right here. You can see the rays coming out from there. And then one other image. This one was taken just on a few days ago, November the 2nd. Again, a similar process, using my BlackBerry up against the lens. And again, you get quite a bit more detail when it's not a full moon. And again, with the BlackBerry, I'm hoping to get a better camera attached to the scope and I get some sharper images. Thank you.
Nicely done. Thanks, Dave. Next. Next. I guess I can do it. Joe. Right button.
So I have just one for you today. This is your friend of mine, M31 in Andromeda. This is 34 2.5-minute light frames taken with unmodified Canon T2i 170 millimeter lens and mounted on a Ioptron Sky Tracker.
Thank you, Joe. Gordon. And Julia. Or Julia and Gordon, actually. Right button. Right button.
Okay, hi. Got to orient myself, they're not in my same order. Okay, some of you have expressed some interest in how I go about doing some of the lunar sketches that I do. These two sketches that I'm going to show you tonight are unfinished. This particular one, the strangest thing happened when I was doing this sketch. It clouded over. Rarely happens. Anyway, the center, where are we? Which one? Right button? No. There we go. Which is the laser? Top one?
Center.
Center. Ah, there we go. Okay, so that would be Kepler here. But what attracted me on this was just the nice arc of similar sized craters moving out there. And it's not showing up well on this because I ran out of time. But what am I trying to say? The ejecta rays, there are about 6 of them coming out from Kepler. Right one. This is, I'll let you guys pronounce that one. But what attracted me on this one, the terminator down here, of course, and was the tiny little crater here on this, I guess it's a wrinkle. Just the series of wrinkles moving away. This is in Mare, what is it, Brian? Humorium? Humorum, okay. And what I'm hoping to do is get a chance to finish these sketches a little more next month, and I'll bring them back and give you a comparison. This is NGC 1275. It's also known as Perseus A. It's a strong radio source in Perseus, and it's the brightest galaxy in the Perseus cluster. And this is done in my backyard in Orleans, right near the park and ride, with all the lights. But we had a really good night, and I actually picked up this galaxy. So, and again, I'm hoping to get out to a darker site, and then hopefully find a few more galaxies right in the same area, because there are a lot of them. And then I've also started playing with some astrophotography. I'm not sure what the red glow in the middle is there, but that's the Veil Nebula, and it's yeah. Thank you. So that's a stack of 8 about 45-second exposures, and it's just done with a standard Canon T3i. Okay, thank you.
So somebody who's just starting to play and get the veil like that, that's well done. Very well done, Gordon. I'm envious, actually. Paul's got some amazing images and videos, as he always does.
Oh, hi, everybody. Cloudy skies, you say, Gordon? Haven't seen many of those lately. What do we do when we have cloudy... Oops. Okay, I had to join the club, right? What do we do when we have cloudy skies at night? Well, we turn to the daytime, and we did have some clear days during the last few weeks where that enormous sunspot group, AR 2192, was quite prominent and easily visible. People were seeing this through with the naked eye when the sun was somewhat obscured through banks of clouds. It was that obvious. So a really interesting object. The largest sunspot group apparently in almost a quarter of a century. So a very interesting object to view. So on October the 24th, I shot this with a couple of different cameras. I used my 11-inch telescope to shoot this and to get a full disk view of the sun. So this was done with a Canon 60DA, and then I switched down. I wanted to get a high-resolution view of the sunspot itself. So to do that, I had to switch cameras, something with a camera with much smaller pixels to get higher resolution without using a Barlow or anything. So using a Celestron NexImage 5. And what that does basically, it's an enhanced video camera, and it allows you to shoot video, which is the way we normally do high-resolution lunar, planetary, and solar imaging. So I wanted to share with you the kind of view that you would get through a telescope if you're looking at this visually, at this object with a high-power eyepiece. We're not in the best part of the world to do high-resolution imaging. We have a lot of turbulence. The seeing is rarely exceptional. So as you'll see from the video, if you can roll the next one there, this is one of the videos that I shot. So I shot 12 video sequences, a total of about 6,000 frames. And you can see how much it varies from moment to moment in terms of the clarity. You'll get those, if you've ever talked to anybody that does observing, high resolution observing, or if you've seen it yourself, you know what we talk about when we say you get those sweet spots. You get those moments of clarity. You get those moments of clarity where things come into sharp focus. And so as you watch the video, and this is looping, this is a sequence of about 250 odd frames from one of the best video sequences I shot. You can see that a lot of them are just junk, right? A lot of them are blurry. That's our atmosphere. But you get the occasional one where it's just right. It's just right. So what I did is I looked at all those video frames, as I said, about 6,000 frames, condensed that down into the best 43 frames. And Chris, if you can roll the next video, this is an amalgamation of the best 43 frames. And I've slowed it down so that you can see more detail in each of the frames. You see, you don't get the same really blurry ones where you can hardly tell what it is. But what we normally do when we do high-resolution imaging is we take a pile of these frames and we stack them, one on top of the other. And what that does effectively is to minimize distortions, increase signal-to-noise ratio, and ultimately you wind up with a clear image. But as I said, this was 43 frames out of 6,000. And as you can see, even these are the best frames of the lot. If I were to try to stack these, and I did, just for the heck of it, it just you don't get anything sharp out of it. It just turns into a blurry mess because it changes so much even within clear frames. And even within one frame to the next, or within a single frame, you'll notice that perhaps the sunspot group on the left is clear, whereas the ones on the other part of the image are distorted. And that's basically just the seeing. Oftentimes in our part of the world, it's actually better to view with a smaller diameter telescope because there you're looking through a smaller column of air. You get less distortions. I was using an 11-inch for this, and who knows, maybe the video would have been a bit more stable with a smaller scope. But anyway, that's what I was running because I wanted to try to get the high-resolution definitions of this. And so what I wound up doing when I realized that stacking wasn't an option, I then distilled those 43 odd frames down to 6 frames, so about 1 out of 1,000 frames. And what I did is I put a mosaic together of those where I'd use parts of one image in one part of the final and then another part. And so I stitched 6 together as a mosaic, not stacked, but more of a stacked or a composite mosaic. And so if you can run the last one there, that's the result from that. So these are individual parts of 6 of the best frames to get the detail. And you can see there is a lot of detail. This was just a glorious thing to look at. You can see there's a lot of gas flowing into the darker areas. You can see some of the granulation on the surface there. Just a lot of spots everywhere. And interestingly, this sunspot group was very, very active. It produced something like 25 M-class flares, half a dozen X-class flares, including an X3. And I'm of mixed minds here because the most powerful X flare that it produced was an X3 class, and it produced that about an hour and a half after I shot this sequence. So I missed out on that, but I did see some images, somebody that took it while it was flaring. For us, the sun was almost near the horizon at the time of that flare, so wouldn't have got very good images anyway. But I saw some images taken from points further west, and much of the central area here was just whited out because of the intensity of the flare. But interestingly, what I found when I learned that this flare had occurred some 65 minutes after I did my imaging, is I looked back and I noticed that this entire area where the flare occurred, even on my images here, looks brighter than the rest. You can see the degree of granulation here and the relative intensity of it, and you can see that the central portion here actually does look brighter. It's almost, I'm just guessing at this, but perhaps the energy was building prior to the eruption, making that area generally brighter, hotter than the other surrounding area. Hard to say. But interesting object there. Hopefully it'll come around again in about 10 days or so. Yeah, Gordon, did you?
Just a quick question. Do you have some trick for focusing when there's that much turbulence in the sea?
You know this trick? Yeah, finger in the wind. It bounces around so much that basically what I do with focusing this is I just look at it for a while and make very minor tweaks and get a gut feel for when you get the most sweet spots. It's tricky. It's tricky to get an accurate focus because it bounces around so a lot. And that's why you have to shoot a lot of frames to get a few that are worthwhile. So this was also done with just out of curiosity, done with a beta filter, same type of filter you use for visual observations, not an H-alpha or anything, just a beta visual filter over my 11-inch scope there.
Hey, Paul, are you recording the local time for each frame?
Yes, I am.
The exact time?
Yeah.
And what time of day do you feel is best for getting the clearest frame?
Oh, it varies completely. Oh, yeah. It not only from day to day, but from minute to minute. Because you get especially on that day, on October the 24th, it was actually quite windy. So I don't know if anybody else was observing on that date, but I think it was actually quite windy if you're out in the open there. So you've got a lot of ground turbulence, turbulence in the air close to the ground, and undoubtedly up the top too to drive those kinds of winds.
So you haven't seen a pattern that shows an ideal time to shoot the sun?
No, I don't think that exists. I think it just varies on the local conditions, and on a larger scale, the jet stream and how it's channeling air masses across the continent, or at least in our part of the world.
Well, how big big does that compare if you were to compare it to the size of Earth?
Funny you should ask that, Eric. That's us in perspective, just to put things in perspective. This was a big, big spot there. So yeah, our little planet there would have easily fit into that large gaping maw there. So anyway, that's what I've got for you there. Hopefully we'll see it in a couple of weeks.
Thank you. Thank you, Paul. Next up is Eric LeMay. Eric?
All right. So I've decided to get into time-lapse photography, and what I'm about to show you here is I think it's about 2 weeks worth of trying to get out in the field and take time-lapse of the Milky Way going across the sky of auroras that happened to be there when I was trying to do some imaging, which if you're out in the field trying to do imaging and the auroras come, I mean, it's nice to see them, but it can get in the way of doing your actual photography. So lately I've decided, okay, well, if it happens, I'm just going to have my camera ready and try to do the photography of it. But anyways, so the images that have gone into this, for those of you who saw Peter Saravello's video earlier tonight of the time-lapse, this is something similar. I used just a regular DSLR, and the images were about 30 seconds long each. So this is about a 2.5 minute long video here. There should be sound here. I don't know why it's not playing. But I guess while he's running up there to play sound, I'll describe this. This was my first attempt, and I mean, I had seen auroras earlier in the night, and then it kind of dawned on me that, well, hey, I'll just shoot the Milky Way going by and see if I can get the auroras. It was done at like ISO. Oh, there we go.
You want to start again?
Yeah, you want it? Yeah, I might as well. Yeah, we're just going to start it over again here. Progressively, as the video goes on, I kind of learned a little more how to do it, and I realized that you can't be doing it at ISO values that are really, really high, just because the amplification is just way too high and you get way too much noise in it, which I had known from doing astrophotography beforehand, but it made it a little more obvious. to put the credits in there, give credit to the guys who made the music as well too. But anyways, so for these last images that were shown in the video, I had originally just put them in there just to show friends and family when I was showing the video of the actual still photography I'd done that night. So the shot that you originally saw in there, this was a bit of a longer exposure that I was able to work on, just this particular frame. The one that you saw, the Milky Way going across the screen with the auroras like that, this was before that video sequence was shot, and the auroras were much, much brighter. So if it had kept up like this, the whole sequence would have been like this. But yeah, I guess you can't be too picky sometimes. You get what you can. Oh, sorry. Next. So this shot right here, I had wandered down the hill because I thought that I might want to frame the cabin in front of the auroras, just to give it a bit more interest. Next. And then this one right here is my scope on the right. Tony Peterson's telescope is on the left. And although his is a bigger scope, it kind of is, it gives you, I mean, mine is a bit farther away, so it looks like it's a lot smaller. But anyways, I guess aperture fever, right? Next. So this one right here now, if I just get up my notes here. So this is an 8-hour-long exposure that I took of the Crescent Nebula in the Hubble palette. And what's going on here, actually, you have a Wolf-Rayet nebula. It's not actually a supernova remnant or a planetary nebula. What you have here is a Wolf-Rayet star that the stellar wind is going out at about 2,000 kilometers per second. So that's about 6 million kilometers per hour. And this stellar wind is brushing up against what do you call it, the mass that had been ejected probably about 250,000 years ago, when it was a red supergiant. So most of the light that comes from this star is actually in the UV range, and it excites the outer walls of the nebula in the oxygen 3 range, which is about 501 nanometers. So the oxygen 3 filter that I use will pick that up really well. And then you have that mass that, as it's expanding out from when it was a supergiant, a super red, or red supergiant, sorry. As that's expanding out, that collides with the interstellar medium. So that creates a lot of heat and causes it to fluoresce in the hydrogen alpha spectrum. And so in doing the Hubble palette, you can see, actually here I'll just use the laser. So you can see predominantly you have a lot of oxygen and hydrogen alpha in this area showing up through the filters. You don't have too much sulfur that shows up. The sulfur, when I talk about Hubble palette, the sulfur will map to red, the hydrogen alpha will map to green, and the oxygen will map to blue. But when you put it together, you end up getting a lot of green throughout the whole image because the hydrogen alpha is so strong. And what you end up having to do is to pull the green down to a more yellowish color, and then you pull the blue down to more of a turquoise color, and you get this result, which is modified Hubble palette, which is more of this gold and turquoise color. So, and then you also have a lot of purple that shows up when you do this. So you have to go through, and you can still see it a bit in the image here, but I was able to get a lot of it out to have this final image here. But this, for those of you who were at Starfest this year, this is the image that I started taking while I was there. It's going to be probably a multi-year project where I stitch about 7 panels wide, 7 panels tall, and I'm going to try to do the whole Cygnus constellation like this. So that's all I've got for tonight. Oh, actually, hold on. I forgot, there's one more here. So this is just a zoom, like a crop into the top right corner. I just wanted to showcase the clouds, the dark clouds in there, and it just gives you a bit of a better idea of the actual color in it. It's a high resolution shot. That's all.
Thank you, Eric. I would love to see more of your material over time, that's for sure. Okay, folks, we're going to close the meeting here. It'll just be 1 minute. I mentioned the telescope clinic sign up tonight if you want to. I think it's wonderful, and again, we're looking for volunteers. We're going to have this over 2 days, as I mentioned. The first date will be the 22nd. You have to pre-register. We're going to have another session, clearly, and possibly even a third. We'll see. I'll keep you posted, particularly people who sign up. I mention always at the end of the meetings that in addition to live streaming of these meetings, we also, the recordings of them are also posted online at Ustream at that address. Just go on Google Ustream Ottawa RASC. Also, some of the older meetings, Eric has been placing them on YouTube. So if you go onto YouTube and just search for Ottawa RASC, you'll see an increasing number of meeting videos that are showing up more and more and more. And there are links that are appearing from our website, ottawa.rasc.ca, to those YouTube. So nice work, Eric, and it's, I guess, a work in progress. Chris reminded me of something. Although Estelle doesn't have a pick of the month, largely because the library is at the Science and Technology Museum, as I mentioned. The Science and Technology Museum is, the library, the physical book library, is actually going to be moving to here, okay, to the Aviation and Space Museum. So that kind of tells you a little bit about how long we might be here at the Aviation and Space Museum. But as you all know, this is quite a nice facility here. Post-meeting social, it's at Perkins Restaurant, just north of Ogilvie Road on Saint Laurent, so not that far from here. It's open to everyone. 105 of us here tonight. Very much thank you to all the speakers and organizers. Actually, I wanted to say one thing before I forget and before I close. That wonderful video that you saw earlier on Comet Hayataki. It was a collaboration by a number of people: Peter Saravolo, John Buchanan, Glenn Ledrew, Paul Boltwood, Glenn. Who else? Doug George. Who else am I missing that was involved with that Comet Hayataki video? Any? Peter Saravolo, obviously, and Glenn I mentioned. So nice. It's held itself very well over time. Nice piece of work, that's for sure. Nice job. I mentioned earlier when the next meeting is, and next month as well. We're going to be. You have to park in parking lot 2. The museum has another event in December the 5th. So they're asking us to park in the parking lot number 2. I'll make an announcement on that. I'm extremely excited about the next meeting, the December meeting. Bob Burnham, many of you know, who writes a series on in Astronomy Magazine. He's an author of many books, and he speaker, and so we're a very gifted speaker. He's going to be here. So I applied for and received a grant from RAC National to cover the cost of bringing him here. Your membership fees are very much a part of this. Bringing people like this. He's a very impressive speaker. I think I mentioned in the last meeting that he has some wonderful material, very engaging speaker. It's going to be over an hour-long presentation. It's only going to be one speaker the next meeting, and it's going to be Bob plus our, member photos and so forth, member images and so forth. But this is going to be a big event. I highly encourage you to come early because I'm going to promote the devil out of this. Okay, so. That's it, folks. And by the way, we've got Carmen Rush is coming back in February to give another one of her presentations on historical figures in astronomy, so I'm looking forward to that too. That closes the meeting, and we'll do the door prizes right now. So folks on the internet, thanks very much for joining us. Feedback's welcome.
Ottawa.